Energy stored in capacitors. If we transfer a small amount of charge, delta Q, from one plate of a capacitor to the other, due to a potential difference V being applied, the energy transferred is given by V delta Q. We can show this on a graph of potential difference against charge. So the small amount of charge here, delta Q, makes negligible change to the potential difference V, and the energy transferred by this transfer of charge is given by the potential difference V times the charge transferred, delta Q. Considering the capacitor charging to a potential difference V consisting of many such narrow strips, the total energy stored on the capacitor will be given by the area under the line here. This then is half the charge Q times the total potential difference V, as the area of a triangle is half the base multiplied by the height. So, copying that equation across to the next slide, we also know that Q is equal to CV, and that V is equal to Q over C. If we substitute this term for Q here, we get that the energy is half CV squared. Also, if we substitute for this term for V here, we get that energy is half Q squared over C. We can use whichever of these three expressions is most useful to us. The energy transferred via the battery will be given by QV. This means only half the energy supplied actually gets stored on the capacitor. The remainder of the energy is lost as heat in the wires as the current flows. Here's a simple example. Calculate the energy stored in a 1000 microfarad capacitor when it's charged to a potential difference of 3 volts. Well, for this we can use energy as half CV squared, and putting in the values, not forgetting the micro here appears as 10 to the minus 6, gives an energy of 4.5 times 10 to the minus 3 joules, or 4.5 millijoules.